566 voltage controlled oscillator circuit. A common type of VCO available in IC form is Signetics NE/SE 566. So this is the pin configuration of NESC 566 voltage controlled oscillator or VCO. So this is the internal structure of VCO. Here we have timing capacitor CT is linearly charged or discharged by a constant current source or sink. The amount of current can be controlled by changing the voltage VC applied at the modulating input by changing the timing resistor RT. A small capacitor should be connected between pin 5 and 6 to eliminate possible oscillations. A VCO is commonly used in converting low frequency signals such as EEGs, EKG into an audible signal. These audio signals can be transmitted over telephone lines or two-way radio communication systems. The voltage across the capacitor CT is applied to the inverting input terminal of schematic trigger A2 via buffer amplifier A1. Capacitor charges and discharges for the same amount of time. This gives a triangular voltage waveform across CT. The square wave output of the schematic trigger is inverted by inverter A3. These are all the various waveforms. First waveform is output at pin 4. Next we have schematic trigger output and output at pin 3 inverted by A3. This is the connection circuit. The total voltage on the capacitor changes from 0.25 VCC to 0.5 VCC. Thus delta V equal to 0.25 VCC. The capacitor charges with a constant current source. So delta V by delta T equal to I by CT, or 0.25 VCC divided by delta T equal to I by CT, or delta T equal to 0.25 VCC CT divided by I. The time period T of the triangular waveform equals 2 delta T. The frequency of oscillator F0 is F0 equal to 1 by T equal to 1 by 2 delta T equal to I divided by 0.5 VC CT. But I is nothing but VCC minus VC divided by RT, where VC is the voltage at pin 5. So if you substitute for I and simplify, we get frequency of oscillation F0 equal to 2 into VCC minus VC divided by CTRT VCC. Voltage to frequency conversion factor. A parameter of importance for VCO is voltage to frequency conversion factor kV, and is defined as kV equals delta F0 divided by delta VC, where delta VC is the modulation voltage required to produce the frequency shift delta F0 for a VCO. If we assume that the original frequency is F0 and the new frequency is F1, then delta F0 equal to F1 minus F0 equal to 2 of VCC minus VC plus delta VC divided by CT RT VCC minus 2 into VCC minus VC divided by CT RT VC. If you simplify this, you get delta F naught equal to 2 delta VC divided by CT RT VCC, or delta VC equal to delta F naught CT RT VCC divided by 2. So now substituting the value of CT RT, we get delta VC equal to delta F naught VCC divided by 8 F naught, or kV, frequency conversion factor kV, equals delta F naught by delta VC, that is equal to 8 F naught divided by VCC. 565 phase locked loop circuit functioning and applications. So this is the IC. The output frequency of the VCO can be written as F naught equal to 0.25 divided by RT/CT Hertz, where RT and CT are the external resistor and the capacitor connected. Short circuit between pins 4 and 5 connects the VCO output to the phase comparator so as to compare F naught with the input signal Fs. So this is the internal connection diagram or functional diagram of the PLL. A capacitor C between pin 7 and pin 10 make a low pass filter. So this is the internal configuration, complete internal configuration. Next we shall briefly see PLL applications, some few applications. First, frequency multiplication division. So this is the frequency multiplier using the PLL IC. The multiplication factor can be obtained by selecting a proper scaling factor N of the counter. A divide by N network is inserted between the VCO output and the phase comparator output. In the locked state, the VCO output frequency F naught is given by F naught equal to N into Fs. Frequency multiplication can also be obtained by using PLL in its harmonic locking mode. If the input signal is rich in harmonics, for example square wave, pulse train, etc., then VCO can be directly locked to the nth harmonic of the input signal without connecting any frequency divider in between. The circuit can also be used for frequency division. It is possible to lock the mth harmonic of the VCO output with the input signal Fs. The output F naught of VCO is now given by F naught equal to Fs divided by M. Next, a frequency translation, which is nothing but shifting the frequency of an oscillator by a small factor. The signal Fs, which has to be shifted, and the output frequency F naught of the VCO are applied as inputs to the mixture. The output of the mixture contains the sum and difference of F naught and Fs. However, the output of low pass filter LPF contains only the difference signal F naught minus Fs. The translation or offset frequency F1 is far lesser than Fs, is applied to the phase comparator. When PLL is in locked state, F0 minus Fs equal to F1, so that F0 equal to Fs plus F1. Thus it is possible to shift the incoming frequency Fs by F1. Next, AM detection. A PLL may be used to demodulate amplitude modulated or AM signals. The PLL is locked to the carrier frequency of the incoming AM signal. So this shows the PLL used as AM demodulator. VCO output is always 90 degrees out of phase with the incoming AM signal under the locked condition. AM input signal is also shifted in phase by 90 degree before being fed to the multiplier. The demodulated output is obtained after filtering the high frequency components by the low pass filter. Output of the multiplier contains both the sum and the difference signals. PLL AM detector exhibits a high degree of selectivity and noise immunity. FM demodulation. If PLL is locked to a FM signal, the VCO tracks the instantaneous frequency of the input signal. The filtered error voltage, which controls the VCO and maintains lock with the input signal, is the demodulated FM output. Next, FSK, frequency shift keying demodulator. In digital data communication, binary data is transmitted by means of a carrier frequency which is shifted between two present frequencies. This type of data transmission is called FSK, frequency keying technique. The binary data can be retrieved using a FSK demodulator at the receiving end. The 565 PLL is very useful as a FSK demodulator. So this is the connection diagram. As the signal appears at the input, the loop locks to the input frequency and tracks it between the two frequencies with a corresponding DC shift at the output. A three-stage filter removes the carrier component and the output signal is made logic compatible by a voltage comparator. Thank you.